Welcome to Wireless Fundamentals, Session 4, Discovering and Connecting to WLANs. The theory you've learned about so far will serve you well, but it is nice to finally be moving toward more practical matters. This lesson is focused on understanding wireless deployment types with a particular focus on the typical WLAN deployment. For such deployments, we'll talk about how endpoints discover and connect to a specific WLAN. An ad hoc network includes two or more stations that communicate directly with each other via their WLAN network interface card, or WNIC. Each station in an ad hoc network receives every packet transmitted. Since no AP or other infrastructure is used, ad hoc connections are inexpensive and easy to establish. They can be used for exchanging files in small meeting areas when access to the wired network is not necessary or possible. However, many organizations consider the use of ad hoc wireless a security risk. An end user could potentially enable an ad hoc network with minimal security, making it easier for hackers to connect and gain access to corporate resources. Later, we'll talk about HP's IMC management platform with the Wireless Services module. This tool allows us to find devices with ad hoc mode enabled, so we can eliminate them and remind the end user that this mode is in direct violation to our corporate policy. A wireless bridge deployment creates a type of WAN link. The AP connects to the corporate infrastructure in one building, perhaps with its antenna mounted on the roof. Ethernet frames on this infrastructure are converted to 802.11 frames, then transmitted and received by the AP installed in another building. This forms a layer 2 connection between the two buildings, connecting two or more LANs. If we need to connect two offices together, perhaps across the street or even a waterway, we could contract a service provider to provide a wired WAN connection for us. They would charge us an initial fee and then monthly for the lifetime of the connection. Instead, we can use a wireless bridge deployment, saving ourselves those recurring charges. If anything ever failed in this connection, we could use a VPN tunnel over the internet as a backup. This makes for a great option when WAN links are not available or are cost prohibitive. While the term in-cell relay mode has been used to describe this type of connectivity, not many WLAN engineers actually use this term. I only mention this in case you run into that rare individual who does. A mesh network deployment is appropriate when you need WLAN coverage, but running data cables to every AP is not feasible. For example, you may need to cover a parking lot with WLAN service. You might be able to mount APs and antennae on existing light poles. The APs can be powered by the same power used for the lights. But digging up the parking lot to run data cables would be very costly. This is a perfect scenario for a mesh deployment. In the figure, two APs are mounted in the building and so can be easily connected to the corporate wired infrastructure. Other APs are mounted in the parking area, using the 5 GHz radio as a backhaul connection. This is how they get connected back to corporate resources. The APs will use algorithms to find the best path back to this infrastructure.
Wait, what kind of algorithms do you mean?
Good question. You may be familiar with routing algorithms like RIP or OSPF. These protocols determine every possible path. Then an algorithm is run using metrics like hop count or cost to determine the best path to a particular destination. Mesh APs determine the best path back to the infrastructure using metrics such as signal quality and perhaps hop count. This is, by the way, the number of APs that must be traversed or hopped over. It is dynamic. If the best path fails, an AP will automatically use an alternate path. End users can connect to any of these APs via the 2.4 GHz radio. The AP accepts client frames on its 2.4 GHz radio and uses the 5 GHz radio to backhaul these frames to the corporate infrastructure. While it is possible to deploy a mesh network using only a single radio AP, this is not advised. Performance will quickly degrade as hop count and user density increases. Infrastructure mode is the most common deployment for wireless networks. This mode simply defines a typical WLAN, in which clients communicate to all other devices via an access point. The AP handles all communication among wireless stations and controls the security and speed parameters for the network. As the interface between the wired and wireless network, the AP receives 802.11 wireless frames from an endpoint, converts them to an Ethernet frame format, and forwards it on to the wireless network. Ethernet frames are received by the AP, converted into 802.11 wireless frames, and transmitted to the appropriate wireless endpoint. This conversion between 802.11 wireless and 802.3 Ethernet frame formats has classically been referred to as a Layer 2 translational bridging function. This is the most common type of deployment and the one we will focus on for most of your training. Let's talk more about how APs make services available to clients in this type of deployment. We can compare a physical Ethernet switch with VLANs to a physical access point with WLANs. Let's do a brief review of these concepts before continuing. Please answer the following questions and submit. Then use the Continue button to move forward. A physical Layer 2 Ethernet switch supports multiple VLANs. A VLAN is a collection of endpoints that share the same network address in the same broadcast domain. You might configure this switch with a VLAN named Corporate and assign 3 ports as members of this VLAN. A DHCP scope can be defined, so users in this VLAN receive an IP address in the 10.0.11.0/24 subnet. You could also define a guest VLAN with 3 member ports. These devices will all have an address in the 10.0.19.0/24 range. If any corporate endpoint sends a broadcast, the switch forwards it out all other ports in the corporate VLAN, but not to any non-member ports. The same thing is true for any other VLAN, such as guest. In this way, corporate and guest users are completely separate, as if they existed on separate physical switches. The only way to enable connectivity between these Layer 2 VLANs is by deploying a Layer 3 device, a router. Most APs include a 2.4 GHz radio and a 5 GHz radio. Each physical Layer 2 radio has its own MAC address and supports multiple VLANs in the form of Service Set Identifiers, or SSIDs. Each WLAN or SSID is analogous to an Ethernet VLAN. Each defines a broadcast domain which is separate and distinct from other WLANs. Technically, a WLAN is defined by an Extended Service Set Identifier, or ESSID. However, everyone simply uses the term SSID, and so that's what we'll say here. I'll use an E in parentheses for a while, just to remind you of the common and technical usages. You could define an SSID named Corporate and use some robust security mechanism, such that only properly configured corporate devices may attach. When you define an SSID, it is assigned a 48-bit MAC address. This MAC address is derived from the radio's physical MAC address and is referred to as the Basic Service Set Identifier, or BSSID. Notice that this BSSID is identical to the radio's physical MAC address, except for the last octet, incremented from :10 to :11. A DHCP scope can be defined to ensure that everyone in this WLAN receives an IP address in the 10.0.11.0/24 subnet. You could also define an SSID named guest. This ESSID receives the next BSSID for that radio. The last octet ends in :12. Endpoints connected to CORP transmit frames to MAC address ending in AA:BB:11, while endpoints connected to guest transmit frames to AA:BB:12. In this way, corporate and guest users are completely separate, as if they were connected to separate physical APs. The only way to enable connectivity between these Layer 2 WLANs is by deploying a Layer 3 router. Let's explore how this all plays out in a corporate AP deployment with multiple APs. Here we see 3 APs, perhaps covering around 7,500 square feet of floor space in our building. All 3 APs support SSID Corp and SSID Guest. We'll focus on Corp for now. When multiple APs support the same SSID, the area of coverage is extended over a wider area, thus the term extended SSID. A corporate employee can connect from anywhere in this extended area of coverage. Although each AP is configured with the same ESSID, each AP has a unique MAC address as assigned by the manufacturer. Therefore, each AP's BSSID is unique. One AP's BSSID ends in :11, another ends in :21, and another ends in :31. A corporate client will initially connect to the closest AP on the left side, in this case, with BSSID ending in BB:11. Each frame transmitted by the endpoint is sent to this AP's BSSID MAC address. As the client walks down the hallway, the signal to BB:11 gets weaker, and the signal to CC:21 gets stronger. At some point, the endpoint's wireless NIC makes the decision to roam or seamlessly connect to the new AP. This happens transparently to the end user with negligible packet loss, if any. The end user simply walks down the hall, perhaps with a mobile device or voice over IP over wireless phone, talking away, unaware that her endpoint is seamlessly bouncing from AP to AP. We'll talk more about roaming later. I just wanted you to have a good understanding of the relationship between ESSIDs and BSSIDs. The same thing is happening for any other SSIDs that may be configured on the APs, including the guest SSID. Clients will initially associate to the AP with the best signal quality, typically the closest one to them. And they'll be able to move freely about the ESSID as they wish. You could sum this up by saying that each AP blankets a particular basic area with RF coverage, and this area is represented by its unique basic SSID. The coverage areas of several APs overlap to extend an area of coverage over a wider area or extended SSID. Again, usually just referred to as the SSID.
Thanks, Vivek. This makes sense. But I'm curious about exactly how clients get connected to an AP. Can we talk about that?
Good question. Let's look at how endpoint devices identify and associate to an AP. Let's take an opportunity to check our knowledge of some key concepts from the material covered so far. Submit your answers to the following questions and use the Continue button to move forward. The first step in getting connected to a WLAN is discovering what APs and SSIDs are available and within range. To do this, endpoints use either passive or active scanning. With passive scanning, endpoints rely on AP beacons. Every 100 milliseconds or so, each AP transmits a beacon frame. This management frame includes information to help the station connect. This includes a list of supported and mandatory data rates, encryption requirements, and most importantly, a list of supported SSIDs. Most endpoints have some type of Find Wireless Networks facility. When you use this facility, you are telling your endpoint's WNIC to passively listen for beacon frames, glean the SSIDs, and display them in a list for you. For example, a Microsoft Windows 8.1 endpoint has a 5 bars icon for wireless. When you click on the wireless bars icon in the system tray, you are shown the available SSIDs based on received beacon frames. You can then select one of these SSIDs and attempt to connect to it. It is not a best practice to let APs advertise corporate SSIDs that are not available to the public. You don't want to tell guests about WLANs they should not access. You will soon learn how to configure WLAN systems so that only guest SSIDs are advertised, while corporate SSIDs are not included in beacon frames. This means that those SSIDs won't be discovered with passive scanning. For active scanning, stations send probe request frames on each channel. Stations can send probe request frames to ask for all supported SSIDs within range, or for a specific SSID. APs that hear the probe request and support the requested SSID will send a probe response frame. The workstation will need to be pre-configured with the corporate SSID so that it will send an active probe request for that specific SSID. On a Microsoft Windows system, the option Connect even if the SSID is not broadcasted can be used to ensure that this occurs. Passive and active scanning help endpoints find available SSIDs. Now they need to connect to those WLANs to use network services. In the original 802.11 specification, there are only 2 mechanisms available to connect. These are called Open System Authentication and Shared Key Authentication. Let's take a look. When a station detects that APs are within range and wireless network access is available, the station begins the process of joining the network. As you just learned, this process often begins with the station sending a probe request. All APs within range receive this request and respond with a probe reply. The endpoint analyzes all of the responses it receives and chooses the one with the best signal strength for connectivity. The endpoint then sends an authentication request. If the SSID has been configured for open system authentication, the AP responds with an affirmative authentication response. In other words, if you ask to authenticate, the answer is yes. This is actually more of a pre-association handshake than an actual authentication mechanism. But don't worry, we'll talk more about robust authentication mechanisms soon. Next, the endpoint sends an association request. The AP receives this request and creates an association ID or AID entry to track this client. This is analogous to a database entry heading. Each AP is responsible for tracking all of its clients. What SSID are they connected to? What is their signal strength? What keys are used for any encryption, etc. This information is tracked under each client's unique AID. The AP responds with an association response, and the client is now connected. These mandatory steps are analogous to plugging in an Ethernet cable. You must plug in your patch cable to connect to an Ethernet switch, like you must discover, authenticate, and associate to an SSID to connect. In both cases, the endpoint will then typically use DHCP to acquire an IP address and then start accessing the network. Because open system authentication does not provide any real security, additional or supplemental authentication methods can be used. These robust security mechanisms ensure that only authorized users are allowed to access the network and protect wireless communications from eavesdropping or tampering. There are a number of options for enforcing supplemental authentication, including WPA, WPA-v2, along with 802.1x EAP mechanisms. We will explore security in greater detail later in your training. For now, let's stay focused on basic 802.11 connectivity. Shared key authentication is the other mechanism built into the 802.11 standard, developed to provide actual authentication for wireless networks. This mechanism, known as Wired Equivalent Privacy or WEP, is easily compromised and is no longer a recommended option for securing a wireless network. WEP depends on APs and endpoints all being pre-configured with an identical key string. The first few steps of shared key authentication are identical to those for open system. Probe request and response, then an authentication request frame is transmitted. This frame contains the station's MAC address and a value indicating shared key authentication. The AP issues a response frame which contains a challenge text, a 128-byte randomly generated data stream. Using the key it should already possess, the station encrypts the challenge text from the AP and sends a challenge response back to the AP. Using the same key, the AP decrypts the challenge text received from the station. If the decrypted challenge text matches that sent in the second frame, the authentication is successful. The AP then sends the final frame in the exchange, indicating authentication success or failure. If successful, the station can proceed to the 802.11 association process, which is identical to that for open system authentication. WEP's shared key encryption method was easy to crack from the beginning, and with widely available freeware circulating on the internet, it is even easier to crack today. As a result, IEEE and the Wi-Fi Alliance have formally disapproved this encryption option, although it remains available to ensure backward compatibility. In contemporary networks, open system authentication is the preferred option. Then, if you need real security, you can implement some form of supplemental authentication. Again, we will discuss these mechanisms during a later session of your training. Let's do a brief review of these concepts before continuing. Please answer the following questions and submit. Then use the Continue button to move forward. Thus far, most of our discussions have focused on understanding WLAN technology. You've learned about various 802.11 standards, as well as antenna concepts and initial client connectivity. We've covered a lot of ground. Why don't we take a short break before moving on? In the next session, we'll begin to focus on actual, real-world deployments. You will learn about WLAN components and the various ways these components can be deployed.